fewer than 24 hours, the third interstellar object ever catalogued will disappear, not in an explosion, nor a gradual fading, but a complete vanishing act, slipping directly behind the sun where no observatory can track it. Scientists term this a solar conjunction. I call it the cosmos drawing its velvet curtain. For the very first time in recorded history, a visitor from beyond our solar system will reach its most dynamically charged moment entirely concealed from our sight. What transpires in that enforced silence? Nobody can definitively answer. So tonight, as two emerald comets illuminate our skies, what some interpret as the universe's deliberate diversion, a third celestial body dissolves into the sun's fiery embrace. Stay with me until the conclusion as we meticulously analyze the impending actions of 3 Atlas. Because the revelations awaiting us at the end will fundamentally alter our perception of extraterrestrial visitors. If this unfolding event has you as captivated and perhaps unnerved as it has me, don't remain a passive observer. Engage with a like and subscribe immediately to ensure you don't miss the subsequent installment of this intricate enigma as it emerges. Share your thoughts in the comments below. Where are you joining us from? What is the current time in your location? And do you believe the truth is being unveiled or deliberately obscured? Furthermore, if you feel this information warrants broader attention, please disseminate it. Broadcast it across X, embed it within your group chats, spread it far and wide, and let us embark on unraveling this mystery collectively. Part 1. The Vanishing Point. Within 24 hours, an event of unprecedented significance will occur. An object originating from a stellar system far beyond our own, identified as 3 Atlas, will traverse behind the sun, rendering it invisible to every terrestrial telescope. This is no ordinary astronomical spectacle that one might overlook by blinking. This is fundamentally different. Neither a comet nor any previously catalogued interstellar visitor has exhibited the behavior Atlas is poised to demonstrate. It will reach the apex of its journey, its closest, swiftest, and most energetically potent phase, while simultaneously becoming utterly imperceptible to us. The scientific community designates this phenomenon a solar conjunction. While the term may sound clinical, even mundane, the reality it describes is anything but. A solar conjunction materializes when the Sun, Earth, and a celestial target achieve a specific alignment, positioning the object virtually behind the Sun from our vantage point. The Sun's overwhelming radiance renders observation not merely challenging, but outright hazardous. Directing a telescope towards the Sun will not yield scientific data. Instead, it risks melting costly equipment. Consequently, we abstain from looking. We are incapable of looking. And for the ensuing weeks, as Atlas hurtles through the most volatile segment of its entire trajectory, we will be entirely deprived of visual observation. Allow me to provide some context. Atlas was first detected on the 1st of July, 2025, by the Asteroid Terrestrial Impact Last Alert System Survey, the same network vigilant for celestial bodies that might pose a threat to our planet. From the moment astronomers began plotting its orbital path, they recognized its exceptional nature. Its orbit was hyperbolic, indicating an origin far outside our own solar system. This classification established Atlas as merely the 3rd confirmed interstellar object ever identified. The inaugural discovery was Oumuamua, that peculiar elongated visitor that navigated our cosmic vicinity in 2017, igniting a multitude of discussions regarding its potential artificial origin. The second was Comet Borisov in 2019, a comet that presented a more conventional appearance, akin to the icy wanderers we are accustomed to observing. However, Atlas is exhibiting behavior distinct from both of these predecessors. Both Oumuamua and Borisov remained visible throughout their closest encounters with the Sun. We were afforded the opportunity to observe them, to measure their properties, and to direct every available instrument towards them, continuously gathering data. With Atlas, however, we will receive no such direct observational data. The object will attain perihelion, its closest point to the Sun, on the 29th of October 2025, at an approximate distance of 203 million kilometers, equivalent to about 1.36 astronomical units. This is the juncture at which its velocity will be at its peak, solar heating will be most intense, and tidal forces will exert their maximum influence. And all of these critical events will transpire while Atlas remains concealed from view. Avi Loeb, the Harvard astronomer whose bold hypothesis suggested Oumuamua might be a solar sail, has characterized this alignment as extraordinary. He has specifically highlighted the precise timing, the conjunction occurring on the 21st of October, followed by perihelion a mere 8 days later, on the 29th of October. These are not events separated by months or years. They are occurring in immediate succession. And I, for one, never hesitate to engage in bold speculation. Pose a simple question that resonates in your mind upon hearing this. Is it a coincidence, or is it deliberate design? Now, before you surmise that this discourse is veering into extraterrestrial speculation, let us establish clarity regarding the nature of the object we are discussing. Atlas is overwhelmingly likely a natural celestial body, a fragment of ice and rock that was expelled from some distant star system eons ago and has been traversing the galaxy ever since. Comets are inherently chaotic entities. Their formation environments are characterized by extreme violence. Being propelled into interstellar space is a rare occurrence, but not an impossible one. We anticipate encountering a few such interstellar travelers over time as our detection capabilities continue to advance. Therefore, the mere existence of Atlas is not inherently astonishing. What is truly remarkable is the timing. Consider it in this manner. Imagine a theatrical performance where the principal actor exits the stage precisely as the pivotal moment of the drama unfolds. The most crucial scene transpires behind the backdrop, while the audience sits in expectant silence. This is precisely the situation we find ourselves in. The most scientifically compelling phase of Atlas's journey, the period when comets typically exhibit their most pronounced activity, when they may fragment, flare, or behave in unexpected ways, will unfold entirely beyond our observational capacity. We do possess certain instruments that might detect ancillary data. Spacecraft such as SOHO, the Solar and Heliospheric Observatory, and the Parker Solar Probe, which has already approached closer to the Sun than any human-made object ever has, might register scattered light or alterations in the solar wind as Atlas makes its passage. The stereo satellites could potentially capture evidence of tail activity. However, these are indirect measurements, mere fragments of information when contrasted with the comprehensive data typically acquired by ground-based telescopes. We will be unable to obtain spectroscopic analysis to examine the gases sublimating from its surface. We will not acquire high-resolution imagery to scrutinize for energetic jets or observable fragmentation. We will not achieve precise astrometric measurements to refine its orbital trajectory, and this is precisely where the tension escalates. Perihelion marks the very instant when comets become most scientifically captivating. The Sun's intense heat vaporizes surface ices, giving rise to spectacular tails and comas. Internal pressures can precipitate sudden outbursts. Structural weaknesses can lead to fragmentation. The comet observed as it approaches the Sun is frequently not the same entity that emerges from its vicinity. We have witnessed comets fracture, observed them dramatically increase in brightness, and even detected slight alterations in their trajectories due to outgassing acting as minuscule thrusters. All of these dynamic processes occur at perihelion. All of these phenomena will befall Atlas while we are incapable of observing them. So, What recourse do we have in the coming 24 hours? Observatories across the globe are engaged in a frantic effort to collect final measurements. These are last looks, concluding snapshots. Every data point obtained now must sustain us through weeks of observational silence. Amateur astronomers, equipped with their backyard telescopes, are diligently capturing their images, acutely aware that while Atlas is faint, it remains technically detectable for those who know precisely where to direct their instruments. The astronomical community is engaged in a race against time, striving to extract every last photon of information from this object before it crosses that intangible boundary and dissolves into the sun's blinding glare. And as we await this moment, as Atlas embarks on its obscured passage, a profound question lingers. What if something extraordinary transpires behind that celestial curtain? What if this interstellar visitor engages in an unexpected action during the singular period when we are unable to witness it? When Atlas reemerges on the opposite side of the Sun in several weeks, will it be the identical object that began this transit? Or will we find ourselves confronting something altered, something distinct, attempting to reconstruct the events of that lost interlude? The countdown has commenced. The vanishing point is imminent, and the heavens are about to be plunged into darkness regarding one of the most extraordinary visitors ever encountered. Part 2. The Silence Window. Let us now consider precisely what we stand to lose. When astronomers state that we will be unable to observe for several weeks, they are not employing hyperbole. They mean it quite literally. This period of invisibility, this silence window, during which 3 Atlas becomes unobservable from Earth, effectively strips away observational capabilities we typically take for granted. You might reason, it's merely a few weeks. We'll catch it on its outward journey. However, you would be overlooking the fundamental significance of this interval. Those few weeks represent everything. Firstly, spectroscopic analysis will cease. Spectroscopy is our primary method for deciphering the chemical composition of celestial bodies. Light that passes through or reflects off a comet's coma and tail is dispersed into its constituent wavelengths, creating a unique spectral fingerprint of elements and molecules. Water vapor, carbon dioxide, cyanide, ammonia, sodium. Each leaves an identifiable mark, revealing the comet's constituent materials, what is actively sublimating from its surface, and its overall level of activity. In the absence of spectroscopy, our understanding of Atlas's composition will be rendered entirely speculative. Should Atlas suddenly begin to release an unusual substance during its conjunction, we will remain unaware. Secondly, we lose the capacity for precise astrometry. Astrometry involves the meticulous measurement of an object's position and motion. With each subsequent observation of Atlas, our comprehension of its trajectory is refined. Minor corrections gradually accumulate, leading to increasingly accurate predictions. However, if the object exhibits any unexpected behavior during this period of obscured observation, any deviation in its velocity or direction, however slight, our pre-conjunction orbital predictions will diverge from post-conjunction observations. We will be left attempting to reverse engineer the events, acting as detectives armed with incomplete evidence. Thirdly, visual observation will be entirely unavailable. We will be unable to ascertain if Atlas undergoes fragmentation. Comets are prone to this phenomenon. They can break apart. This fragmentation can occur gradually, with pieces detaching like icebergs calving from a glacier, or it can be a catastrophic event, resulting in the nucleus shattering into numerous fragments that disperse along its orbital path. If Atlas fractures during perihelion, we will not witness the event itself. We will only observe the aftermath, a field of debris where a single object once existed, and we will be forced to conjecture about the mechanisms and timing involved. This confluence of perihelion and conjunction presents a significant challenge. Perihelion is precisely when cometary activity reaches its zenith. The object is traveling at its maximum velocity, often exceeding 100,000 kilometers per hour relative to the Sun. Solar heating is at its most intense. Thermal stress is at its peak. Tidal forces, the gravitational stretching effect, are also maximized. This is the moment of greatest potential drama, and it is precisely this moment that will elude our observation. Consider this analogy. Imagine you are observing a car race, and the most critical section of the track, the part where drivers push their vehicles to the absolute limit and the likelihood of accidents is highest, is obscured from view behind a large building. You see the cars enter this obscured zone, and you see them emerge, but you have no insight into what transpired in between. Did a car spin out? Did another car gain an insurmountable lead? Did an impossible maneuver occur? You will only learn of these events through the subsequent outcomes, and even then your understanding will be based on inference. Historically, other comets have passed behind the Sun. This is not an unprecedented occurrence. However, none of these prior instances involved interstellar visitors reaching perihelion during a conjunction. None of them carried the same inherent mystery as Atlas. All previous cases involved objects that we had tracked for many years, objects with predictable orbital paths and well-understood behaviors. Atlas is different. We have been aware of its existence for less than 4 months. We are still in the process of understanding its fundamental nature, and now we are about to lose visual contact at the most inopportune moment. The practical consequence of this period of obscured observation is that numerous observatories will redirect their focus. Why allocate valuable telescope time to an object that cannot be seen? Other celestial targets will naturally assume priority. The economic realities of funding and scheduling necessitate operational efficiency. This means that when Atlas eventually reappears, there may be a delay before observational efforts are fully re-established. Opportunistic observers, including amateur astronomers and smaller institutions, might be the first to reacquire it. Professional networks will subsequently follow, but those initial days immediately following its reappearance are crucial, and we risk missing vital details if there is a slow collective response. Furthermore, there is a psychological dimension to consider. Scientists rely on continuous observational data to build confidence in their predictive models. Gaps in this data introduce inherent uncertainty. The longer the observational gap, the greater the uncertainty becomes. When dealing with an interstellar object, something that is inherently anomalous by its very definition, uncertainty breeds discomfort. Scientists desire concrete data, corroboration, and the ability to systematically eliminate improbable explanations. The silence window fundamentally impedes this process. And let us address the unspoken question: what if something intentional occurs during the conjunction? I am not asserting that it will. I am not claiming Atlas is artificial. However, the question itself arises, whether we find it palatable or not. If one were tasked with designing an interstellar probe and wished to execute a specific action without detection, the perihelion during a conjunction would represent the ideal temporal window. It offers access to maximum energy, peak velocity, and complete invisibility from Earth. One could deploy secondary probes, adjust the trajectory, or perform a multitude of actions that would be readily apparent if observed, but which will go entirely unwitnessed. Again, natural explanations remain the most probable. Outgassing, fragmentation, thermal fracturing. These are all well-understood natural processes. However, the precise timing creates a void in our narrative, and such voids inevitably invite speculation. The more prolonged the void, the greater the ensuing speculation. By the time Atlas reappears, numerous hypothetical scenarios will have been formulated, and we will lack the empirical means to confirm or refute the vast majority of them. The silence window, therefore, does not merely conceal the object, it conceals the truth. Consequently, we are left with a period of patient anticipation. The object disappears from view. Weeks elapse. Solar observatories may capture fleeting hints, perhaps if fortune favors us. Ground-based telescopes remain idle, their attention diverted to other celestial regions. And somewhere beyond the sun, shrouded by glare and immense distance, Atlas continues its journey, accelerating, heating, potentially transforming, or perhaps remaining unchanged. We will not know which until its passage is complete. The curtain has descended, the lost act has commenced, and whatever unfolds next will occur in utter darkness. Part 3. Orbital Puzzles. Now let us delve into a peculiar aspect of Atlas's trajectory. When an interstellar object enters our solar system, we anticipate its arrival from virtually any direction. Space is a three-dimensional expanse. There is no inherent preferential orientation. Objects should ideally arrive from above the solar system's plane, from below it, at steep angles, or scattered randomly across the celestial sphere. However, Third TUI Atlas deviated from this expectation. It entered our solar system in near alignment with the ecliptic plane, with a tilt of only approximately 5 degrees relative to the orbital plane of Earth and the other major planets. This is an unusual characteristic. The ecliptic plane represents the relatively flat disk within which Earth and the primary planets revolve around the Sun. If you envision our solar system as a dinner plate, the ecliptic plane corresponds to the surface of that plate. The majority of solar system objects reside in close proximity to this plane, a consequence of their formation from a common rotating disk of gas and dust billions of years ago. Interstellar visitors, by definition, did not originate within our solar system. They possess no inherent reason to conform to our planetary plane. Their arrival angles should therefore be random. So, why is Atlas so precisely aligned with the ecliptic? It is possible that this is a mere coincidence. Statistical probabilities allow for outliers. If you flip a coin 100 times, it is not uncommon to observe 10 consecutive heads. This does not imply the coin is biased. Atlas could simply be that singular object that happened to enter along the ecliptic by sheer chance. However, when one begins to tally the accumulating coincidences, the precise arrival angle, the synchronized timing of conjunction and perihelion, and a trajectory that brings it in proximity to several planets while obscured from view, the notion of pure serendipity becomes increasingly difficult to accept. Astronomers have attempted to retroactively trace Atlas's orbit to determine its point of origin. This involves taking its current trajectory, applying gravitational calculations backward through time, and observing if these calculations point to any known star system. This methodology is effective for certain interstellar objects. For instance, Borisov's trajectory could be broadly correlated with a region of space consistent with its ejection from a young star system. However, in the case of Atlas, no clear origin is discernible. The backward trace generally points towards the constellation Sagittarius in the direction of the galactic center, but the data does not yield a specific parent star. It is as if the object materialized from an unknown source, or from a location so distant and so profoundly influenced by galactic gravitational forces that pinpointing its origin becomes impossible. Furthermore, there is the matter of its velocity. Since Atlas was discovered in July, observers have diligently collected astrometric data to refine its orbital parameters. Some of these data points suggest that the object is moving at a velocity slightly exceeding that predicted by purely gravitational models, or that its trajectory exhibits subtle non-gravitational influences. This could be attributable to outgassing, a common phenomenon for comets. When ice vaporizes from one side of the cometary nucleus, it generates a propulsive effect akin to a miniature thruster, subtly altering the comet's course. We observe this phenomenon regularly. However, with Atlas, the observed deviations are minute, and we have not been observing it for a sufficient duration to definitively ascertain their cause. Is it natural outgassing, internal activity, or something else entirely? Let us address the perihelion distance. Atlas will reach its closest approach to the Sun at approximately 1.35639 astronomical units, which translates to roughly 203 million kilometers. This distance places it comfortably outside Earth's orbital path, which is defined as 1 astronomical unit. It is closer than Mars, but not dramatically so. The specific time of this closest approach is the 29th of October 2025 at 11 hours, 34 minutes, and 35 seconds terrestrial time. The very precision of this measurement is, in itself, noteworthy. We are capable of calculating orbits with remarkable accuracy when we possess an adequate amount of observational data. However, all such precision is predicated on the assumption that the object behaves in a predictable manner. If Atlas were to exhibit any unforeseen behavior during its conjunction, our meticulously calculated perihelion time might prove to be slightly inaccurate, and we would only discover this discrepancy after the event has passed. Here is where speculation becomes more pronounced, and I wish to emphasize that this is indeed speculative. Certain recent academic papers in the field of astrophysics explore the concept that galactic structure might create what could be described as gravitational corridors. These are not physical conduits, but rather regions of space where the combined gravitational influence of stars, nebulae, and dark matter creates pathways characterized by marginally reduced gravitational resistance. Objects traversing these corridors might follow similar trajectories across vast cosmic distances, much like rivers flow through valleys. This is a fringe theory, not yet established as mainstream scientific consensus, but it is indeed under investigation. If such corridors exist, they could potentially explain why multiple interstellar objects might arrive from similar directional vectors. The hypothesized Sagittarius corridor, if it indeed exists, could represent one such pathway. Let us be candid about the situation at hand. The most straightforward explanation is the natural one. Atlas is an ancient comet that was ejected from its home system millions of years ago and has been drifting through the galaxy until it happened to pass through our cosmic neighborhood. Orbital dynamics are inherently complex. Gravitational interactions occurring over extended periods can so thoroughly scramble trajectories that tracing them back to their origin becomes an insurmountable task. The alignment with the ecliptic could be a matter of chance. The precise timing of events could also be coincidental. The observed velocity anomalies could be explained by standard outgassing phenomena. All of these are reasonable and defensible interpretations. However, the alternative explanation persists, and to ignore its existence does not make it disappear. If Atlas were artificial, if it were a probe engineered by an intelligence possessing the capability for interstellar travel, its observed trajectory would make considerably more sense. One would strategically choose to enter a star system along the ecliptic, because that is where the planets are situated. One would select the moment of closest approach during a conjunction to maximize available energy while minimizing the risk of observation. One would aim to pass in close proximity to multiple planets, such as Mars, Venus, and Jupiter, while concealed in order to gather data or deploy smaller instrumental payloads. This is not definitive proof, nor is it even conclusive evidence. It is merely an observation that an engineered trajectory and the observed trajectory bear a striking and potentially significant resemblance. Avi Loeb has provocatively suggested that Atlas warrants serious attention, not because it is definitively artificial, but because the convergence of unusual circumstances suggests that we should not dismiss the possibility without rigorous investigation. The majority of astronomers disagree with this assessment. They correctly point out that extraordinary claims necessitate extraordinary evidence, and such evidence is currently lacking. An unusual orbital path alone is insufficient. Peculiar timing in isolation is also insufficient. What is required is a definitive indicator, a clear techno-signature, something that cannot be explained by natural phenomena. And thus far, we have not identified such a definitive marker. However, herein lies the inherent tension. The definitive indicator, if one exists, might manifest itself precisely during the period when we are unable to observe. If Atlas is poised to perform an artificial action, to alter its course, deploy instruments, or transmit a signal, it would likely do so during the conjunction, and we would consequently miss the event. By the time the celestial body reappears and we can observe it anew, the opportune moment will have elapsed. We will be left with visual records of its prior and subsequent states, endeavoring to comprehend what transpired in the interim. Thus, the enigmas of its orbital path persist. From whence did Atlas originate? What dictates its alignment with the plane of Earth's orbit? What accounts for the deviations in its velocity? Are we witnessing an incidental celestial visitor or something intentionally positioned? Its trajectory may hold profound revelations, but these secrets are poised to become considerably more elusive. Part 4. The firmament's counterpoint. As 3 Atlas readies itself for its departure, the nocturnal expanse is not conducive to a somber disposition. Indeed, around the 20th of October, the heavens put on a remarkable display. 2 luminous comets, Comet C 2025-A6, recognized as Lemmon, and Comet C 2025-R2, designated SWAN, are both discernible to onlookers within the northern hemisphere. If one possesses the knowledge of where to direct their gaze and is fortunate enough to experience unpolluted, dark skies, they may perceive their emerald luminescence shortly after twilight. It presents a peculiar juxtaposition. 2 comets illuminating the sky while one is vanishing. Comet Lemmon was first sighted on the 3rd of January, 2025, by observers utilizing the Mount Lemmon survey in Arizona. Since that discovery, it has steadily increased in brightness as it draws nearer to Earth. On the 21st of October, precisely as Atlas achieves conjunction, Lemmon reaches its closest proximity to our planet at an estimated distance of 0.6 astronomical units, equivalent to approximately 90 million kilometers. This proximity, while not exceptionally close by cometary standards, is sufficient such that under conditions of darkness, far from urban light pollution, the comet should be apparent to the unaided eye. Observers have noted a greenish tint, a result of diatomic carbon-emitting light when exposed to the sun's rays. This is a characteristic hue for comets, the kind that compels individuals to pause and marvel. To witness Lemmon, direct your attention toward the northwestern horizon once the sun has set. It will not be positioned high in the sky, perhaps 15 or 20 degrees above the horizon, necessitating a clear, unobstructed view. Binoculars can prove beneficial if you are situated in an area with significant light pollution. Through a pair of binoculars, the comet manifests as a nebulous greenish cloud, potentially accompanied by a faint tail extending away from the sun. It will not resemble the dramatic depictions of comets found in academic texts, which are often captured through extended exposure photography. Visual observations of comets are more subtle, yet there is an elemental allure in perceiving one with one's own senses, recognizing it as a composite of ice and dust from the outer reaches of the solar system, shedding its constituents as it warms. Then there is Comet SWAN, discovered more recently on the 10th of September, 2025, by the Solar Wind Anisotropies instrument aboard the Solar and Heliospheric Observatory. SWAN excels at detecting hydrogen emissions, which aids in its capacity to identify comets prior to their achieving sufficient brightness for ground-based detection. This particular comet attains its closest approach to Earth around the 21st of October as well, at an approximate distance of 40 to 50 million kilometers. It will be situated low in the southwestern sky after sunset, presenting another viewing opportunity during twilight. SWAN's visibility is less assured than that of Lemmon. Predictions suggested it might achieve naked-eye visibility, But comets are inherently unpredictable. They possess the capacity to suddenly intensify or, conversely, diminish in brilliance. As of the middle of October, reports indicate that SWAN is observable, though faint, necessitating the use of binoculars or a small telescope. Nevertheless, the concurrence of two comets reaching their peak visibility around the same time as Atlas's conjunction creates a compelling visual narrative. Look skyward on the 20th or 21st of October. You might observe two visitors from the distant solar system, both reflecting solar radiation, both expelling matter, both putting on a celestial display. And while you are observing them, bear in mind that a third traveler, one originating from an entirely different star system, is stealthily departing from view. Furthermore, the Orionid meteor shower, which typically peaks around the 20th and 21st of October annually, should be noted. The Orionids are composed of detritus from Halley's Comet, minuscule particles dispersed along its orbital path through which Earth annually traverses. Upon entering Earth's atmosphere at a velocity of 70 kilometers per second, these particles vaporize, creating luminous trails, which we identify as meteors or shooting stars. The Orionids are not the most prolific meteor shower, perhaps yielding 20 meteors per hour under optimal circumstances, but they are exceptionally swift and often leave persistent luminous traces. If you are already outdoors observing the comets, you may well witness a few meteors streaking across the celestial dome. Consequently, the sky on the 20th of October presents a dynamic scene. Lemmon gracing the northwest, SWAN in the southwest, and Orionid meteors radiating from the constellation Orion in the east. It resembles a celestial traffic confluence, with multiple phenomena vying for your attention. And somewhere behind the sun, imperceptible and unnoticed by the majority, Atlas continues its obscure journey. There exists a thematic contrast here that warrants consideration. Lemmon and SWAN are readily visible. They are accessible. Any individual with an unobstructed horizon and a pair of binoculars can observe them. They form part of the shared human experience of contemplating the night sky, an experience our forebears have engaged in for millennia, tracking comets and weaving narratives around them. Atlas, conversely, is invisible. It is known solely through empirical data, through computational analyses of its orbit and sophisticated scientific instrumentation. A great many individuals are unaware of its existence, and the few who are privy to its presence cannot behold it. It is concealed not only by the sun, but by its very nature, an interloper from beyond our solar system, operating on a scale and following a trajectory that defies straightforward observation. One might contend that the two visible comets serve as a diversion. While amateur astronomers worldwide direct their telescopes toward Lemmon and SWAN, and social media becomes inundated with images of the green comets, Atlas proceeds with its clandestine activities, unobserved, out of sight, out of mind. The spectacle captures the eye while the true narrative unfolds elsewhere. Perhaps this is an overanalysis. It is possible that the convergence of three comets within the same observational window is merely a matter of chance. However, coincidences are accumulating, and at some juncture one must begin to question their nature. If you venture outdoors to observe the comets, take a moment to reflect on what you are witnessing. Lemmon and SWAN are indigenous to our solar system, likely ejected from the Kuiper belt or the Oort cloud due to gravitational disturbances. They have been in orbit around the sun for eons, venturing into the frigid darkness and then swinging back toward warmer regions. Atlas is distinct. It has arrived from external space. It is merely passing through, never to return, following a hyperbolic trajectory that will ultimately convey it back into interstellar realms. Three comets, two observable, one not. Two that belong within our celestial neighborhood, one that does not. The sky acts as a mirror, presenting a duality of visibility versus invisibility, spectacle versus stealth. the apparent versus the concealed. And as Atlas retreats behind the sun, as the night sky is illuminated by its more cooperative celestial kin, we are reminded that often the most significant elements are those beyond our immediate perception. Part 5. The Countdown. We are now mere hours away. Less than 24 hours remain until 3, i.e. Atlas, traverses the unseen boundary and becomes unobservable from Earth. This constitutes the critical decision period, the final opportunity to acquire data before the silence descends. Across the globe, observatories still capable of tracking Atlas are engaged in a frantic effort. Final spectral analyses, last photographic captures, concluding astrometric measurements. Every captured photon is invaluable. Telescope time is a valuable and highly sought-after commodity. Major observatories schedule their allocations months in advance. Proposals are submitted, requiring justification for why a particular target merits the allocated time, followed by a period of waiting for approval. However, when an urgent situation arises, when an object of significant interest is on the verge of disappearing, the established system can demonstrate flexibility. Certain observatories maintain directors' discretionary time slots reserved for observations that are time-sensitive. Atlas qualifies for such consideration. This represents an unprecedented event, the first interstellar object to complete its perihelion during conjunction. If we fail to observe it now, the opportunity will be lost forever. Amateur astronomers are also playing a crucial role, and this contribution deserves recognition. One does not require a facility valued at billions of dollars to make a contribution. With a respectable backyard telescope, a CCD camera, and some processing software, one can acquire astrometric data or photometric measurements that will be utilized by professional scientists. The community dedicated to asteroids and comets relies on a global network of observers, many of whom are enthusiasts who meticulously track celestial bodies and report their findings. When an object such as Atlas appears, amateur astronomers mobilize. They exchange positional coordinates. They compare their observations. They disseminate images online. This exemplifies citizen science at its finest, a collaborative endeavor to extract the maximum possible information from a fleeting opportunity. However, there are circulating rumors, and it is at this point that the situation becomes less clear. Certain reports suggest that spectroscopic examinations of Atlas have yielded unusual compositional data that has not yet been publicly disseminated. These are results held under embargo, awaiting peer review. The specifics remain vague: a lower water content than anticipated, peculiar ratios of nickel or cyanide. Nothing conclusive has been established, nor has anything been formally published. These are merely whispers within the astronomical community. Are these rumors credible? It is difficult to ascertain. Scientific progress is often a gradual process. Preliminary findings frequently do not withstand rigorous scrutiny, but the rumors persist and contribute to the mystique. Why would the composition be significant? Because it informs us about the constituent materials of the object, which in turn indicates its origin. Comets originating from the outer solar system possess distinct chemical signatures. Comets from the inner regions exhibit different characteristics. Interstellar comets are theoretically expected to display compositions reflecting their genesis, potentially enriched in certain volatile compounds or depleted in others, contingent upon the conditions prevalent in their home system. If Atlas's spectrum genuinely deviates from the norm, if it does not align with any known population of comets, that would constitute a scientifically significant discovery. It would imply formation conditions previously unencountered. Or, if one is inclined towards conjecture, it could suggest something entirely different. However, let us refrain from premature conclusions. Unverified rumors are merely unsubstantiated claims until they are corroborated. The scientific process is designed for a reason. Data must be meticulously checked, re-examined, subjected to peer review, and formally published before it can be accepted as factual. Until such time, we are left with speculation, which, while entertaining, is not a reliable basis for understanding. For those of you equipped with a telescope, Atlas remains technically observable, albeit faintly. Magnitude estimations place it around 13 or 14, far beyond the capability of naked eye observation. You will require a telescope of considerable aperture, at least an 8-inch lens, and precise knowledge of its location. Ephemerides, which are tables detailing predicted positions, are accessible through the Minor Planet Center and various other sources. Direct your telescope, employ a prolonged exposure, and you may succeed in capturing one of the final images of Atlas before its disappearance. Will it hold significant scientific value? Likely not in a purely scientific sense. However, there is a profound meaning in participating in its observation, even in a minor capacity. As the hours dwindle, a discernible psychological shift occurs among those who are attentively following the event. A blend of anticipation and apprehension pervades. We are on the cusp of entering a period of uncertainty. The object will continue its celestial journey, but our connection to it will be severed. It is akin to observing someone enter a tunnel. You see them disappear into its depths. You wait. In due course, they are expected to emerge on the other side, but while they are within, while they are concealed, one cannot help but ponder what is transpiring therein. Are they unharmed? Have they undergone a transformation? Has something changed? The tension is amplified by the fact that this is not merely any celestial body. This is a visitor from beyond our stellar neighborhood. It is only the third confirmed instance of such an occurrence. These events are exceedingly rare. We are uncertain about the frequency with which they traverse our galactic vicinity. We do not know if we will encounter another one next year or in the next century. To miss this particular instance, to miss the most compelling phase of its journey, feels like a colossal missed opportunity on a cosmic scale. And then there is the timing. Its perihelion occurs 8 days after conjunction. Maximum velocity, peak energy, and intense heating all transpire while it is hidden from view. If one were crafting a suspenseful narrative, such a scenario could not be more effectively devised. The protagonist enters the zone of peril precisely as the cameras cease their recording. What transpires next will be revealed upon the protagonist's emergence. However, until that moment, we are left in a state of suspense. Therefore, what will we do with the period during which Atlas remains concealed? The majority of individuals will simply forget about it. Life progresses. New cycles commence. The narrative fades into the background hum of existence. But for those who are observing, for those who comprehend the implications of these events, the period of waiting itself constitutes the narrative. The silence becomes the plot. And the fundamental question, what will Atlas resemble when it reappears, emerges as the compelling element that sustains our engagement. In mere hours, the countdown will conclude. The object will cross into conjunction, and our visual access will be extinguished. For several weeks, we will endure this period of darkness, harboring the hope that when light is once again shed upon it, the unfolding story will resonate with logic, and that the object emerging will be identical to the one that entered. We hope that the answers we uncover will align with our initial expectations. However, hope and expectation are distinct sentiments, and within the vast expanse of space, events rarely conform precisely to our desires. Part 6. The Sagittarius Corridor Hypothesis. Let us broaden our perspective and examine a phenomenon that may not be a pattern at all. Several anomalies, including Three-Eye Atlas, Oumuamua, and the renowned WOW signal of 1977, all appear to originate from the general vicinity of the constellation Sagittarius. This direction corresponds to the galactic center, the densely populated nucleus of our Milky Way galaxy. Does this hold any significance, or are we engaging in a fundamentally human practice of discerning patterns within random occurrences? The Sagittarius corridor hypothesis, and I wish to emphasize that this is speculative, posits that certain directions within the galaxy might serve as preferred conduits for interstellar objects. Consider it in this manner. On Earth, we construct roads where the terrain is amenable. Rivers carve valleys. Animals follow established routes. We gravitate towards paths of least resistance. Could a comparable phenomenon be occurring on a galactic scale? Gravitational wave cartography, a relatively recent discipline in astrophysics, maps the large-scale structure of space-time as influenced by massive objects. Galaxy clusters, supermassive black holes, and dense molecular clouds all exert gravitational influences that warp space-time in ways we are now capable of detecting and modeling. Some researchers propose that these warps create conduits, regions where an object traversing space encounters marginally diminished gravitational interference. It is not that the fabric of space-time is physically altered, but rather that the cumulative distribution of mass creates pathways into which objects might naturally gravitate over millions of years. If this proposition holds true, and this is a significant if, then objects entering our solar system from the direction of Sagittarius may be following such a conduit. Atlas entered our system aligned with the ecliptic, with a tilt of approximately 5 degrees. Previous interstellar candidates have also exhibited trajectories that broadly align with this general direction. The trajectory of Oumuamua, when traced backward, vaguely pointed towards the galactic plane. The WOW signal, that brief radio transmission detected by Ohio State's Big Ear telescope on August 15, 1977, originated from Sagittarius. When these instances are aggregated, a cluster of intriguing events becomes apparent, all associated with a particular region of the sky. However, correlation does not imply causation. Sagittarius is an extensive constellation, occupying a substantial portion of the celestial sphere. The galactic center resides in that direction, implying a greater concentration of matter, more stars, and thus more potential source regions. Furthermore, it is often towards this area that we direct our telescopes when searching for unusual phenomena. Selection bias is a significant concern in astronomy. We tend to find what we actively seek, and we focus our search in areas where we anticipate discoveries. Therefore, it is plausible that the Sagittarius connection is merely an artifact of our observational focus. Nevertheless, the concept of a galactic corridor is indeed compelling. If advanced civilizations exist and engage in interstellar travel, they might very well utilize these conduits in a manner analogous to our trade routes. Such pathways would represent low-energy, efficient, and predictable means of transit. One would not launch a probe in a random direction. Rather, one would target a conduit that enhances the probability of encountering something of interest. Earth is situated within the galactic plane, in a region characterized by active star formation. If one were traveling along the Sagittarius corridor, our solar system would eventually lie within its path. This raises a question that many scientists find disquieting. Are we observing natural debris drifting along gravitational pathways, or are we witnessing engineered objects utilizing those same pathways with deliberate intent? The underlying physics remains consistent in either scenario, whether natural or artificial. The observed trajectory would appear similar. An engineered probe would not necessarily exhibit any overt artificial characteristics. It would simply follow the path of least resistance, blending seamlessly with natural travelers. Avi Loeb has articulated this perspective in his writings. He is not asserting that Atlas is artificial, but rather that its trajectory and timing are consistent with the predictable behavior of an artificial object, thereby warranting thorough investigation. The majority of his colleagues express reservations, arguing that invoking extraterrestrial intelligence without direct evidence is premature. They are, of course, correct. Extraordinary claims necessitate extraordinary evidence. However, Loeb's counterargument is that by failing to investigate, by dismissing possibilities simply because they seem improbable, we risk never discovering evidence, even if it exists. The wow signal warrants re-examination in this context. On August 15, 1977, the Big Ear radio telescope at Ohio State detected a strong, narrow-band signal that persisted for 72 seconds. The signal was so unusual that astronomer Jerry Eman inscribed the word "wow" in the margin of the printout, giving the event its enduring name. The signal originated from the direction of Sagittarius, specifically near the constellation Chi Sagittarii. Subsequent attempts to reacquire the signal have been unsuccessful. 48 years later, its origin remains unknown. Was the wow signal artificial? It is possible. Was it natural? Also possible. Could it have been terrestrial interference? Perhaps. The pertinent point is that we do not possess a definitive answer. The fact that it emanated from approximately the same direction as some interstellar objects adds an intriguing layer of curiosity. If one were to engage in a process of connecting the dots, Sagittarius presents a multitude of them. However, caution is advised. Drawing lines between disparate events is the genesis of conspiracy theories. The wow signal and Atlas are separated by nearly 50 years and involve entirely distinct phenomena. One is a radio signal, the other a physical object. To link them necessitates assumptions for which we lack justification. At best, we can acknowledge the coincidental directional alignment and file it away as an interesting observation, though not conclusive. The corridor hypothesis also possesses naturalistic explanations. The galactic center exerts a dominant gravitational influence. Objects in its vicinity experience more pronounced tidal forces and exhibit more complex dynamics. Material ejected from star systems located near the center may naturally disperse along specific trajectories dictated by the combined gravitational pull of billions of stars. Over millions of years, a population of objects could accumulate, traveling along preferred paths, not due to artificial design, but because gravity shapes their motion. So, where does this leave us? The Sagittarius corridor is a hypothesis, not a rigorously established theory. It represents an idea that warrants investigation but remains unproven. The alignment of Atlas, Oumuamua, and other anomalies might be significant, or it could be a manifestation of coincidence amplified by the human propensity for pattern recognition. We require additional data. We need to track a greater number of interstellar objects. We require more sophisticated models of galactic structure and gravitational dynamics. At present, our sample size consists of 2 confirmed interstellar objects, possibly 3 if we include Atlas. This is insufficient to definitively establish a pattern. However, this is precisely what makes the current situation relevant to Atlas's conjunction. If the object is adhering to a natural corridor, then its passage through our solar system is simply a consequence of physical laws in operation. If it is following an engineered route, if the corridor is being deliberately utilized, then the timing and trajectory assume a different level of significance. The fact that Atlas reaches perihelion while obscured from view could be interpreted as a deliberate navigational strategy rather than a cosmic accident. We will not resolve this particular question during its conjunction. We will not resolve it when Atlas reemerges. It is possible that we may not resolve it for decades. However, the question itself remains, awaiting an answer. Are we observing random travelers from the vast cosmic wilderness? Or are we witnessing traffic on a galactic highway? Objects moving with apparent purpose along established routes. The corridor hypothesis offers one framework for contemplating this mystery. It suggests that space is not as empty and chaotic as we often assume, but rather that there exist structures, pathways, and patterns that we are only beginning to discern. And if these celestial pathways are indeed present, if the vastness of our galaxy contains roots carved by gravity and the passage of eons, then perhaps our sense of solitude is an illusion. It's conceivable that the distances between stars are traversed far more frequently than we currently comprehend. And with that thought, perhaps, just perhaps, we are finally beginning to acknowledge this cosmic transit. This brings us to Part 7, the data suppression conundrum. We must now address a topic that invites discomfort. Within certain online communities and among some enthusiasts of astronomy, a dialogue is taking place concerning the potential withholding of observational data. The assertion is straightforward yet significant, that information pertaining to specific celestial bodies, particularly those exhibiting unusual or anomalous characteristics, is subjected to delays, classification, or outright retention by governmental space organizations and scientific institutions. Is this truly occurring? And if so, what might be the underlying reasons? Let us begin with established facts. In principle, the practice of astronomy relies on a system of peer review and the subsequent public dissemination of findings. Once an observation is made, the expectation is that it will eventually be published. Dedicated data repositories are maintained with the express purpose of making information accessible to the worldwide scientific community. The Minor Planet Center meticulously compiles astrometric measurements. Sky survey projects generously provide imaging data. Spectroscopic archives serve as repositories for chemical analyses. This fundamental openness is the bedrock upon which scientific progress is built. The ability to independently verify discoveries hinges on access to the raw data. However, exceptions do exist. Certain observations are subject to proprietary periods, during which the research team responsible for gathering the data is granted exclusive rights to analyze and publish their findings for a predetermined duration before public release. This is a well-established convention. If an individual or team has dedicated years to developing an instrument and months to collecting data, they are afforded the initial opportunity to interpret and share their results. These proprietary periods can extend for several months or even a full year. Throughout this interval, the data remains private, inaccessible to other researchers. Can this be construed as suppression? Not precisely. It is, in essence, a mechanism for safeguarding intellectual investment. Nevertheless, from an external perspective, it can certainly appear as if information is being deliberately concealed. Beyond this, considerations of national security come into play. Both ground-based observatories and orbital assets occasionally detect objects that governments deem sensitive. This could include military satellites, debris originating from classified missions, or near-Earth objects that pose a potential impact threat before effective mitigation strategies can be formulated. In such circumstances, data may legitimately be classified or its release postponed to prevent widespread public apprehension or to avoid revealing operational capabilities. Does this scenario occur? Almost certainly. The frequency of such occurrences is difficult to ascertain. The very nature of classification implies that we are unaware of what information is being withheld. Regarding the object known as Atlas, there are unsubstantiated rumors circulating, without verifiable sources, suggesting that some spectroscopic data has been intentionally withheld. The stated justification for this is that preliminary findings necessitate confirmation prior to their official publication. This is a perfectly valid scientific practice. It is prudent to avoid announcing significant discoveries based on uncertain or noisy measurements, only to be forced into a retraction later when more robust data reveals an error. Science has, in the past, been tarnished by premature announcements, such as the initial claims of cold fusion, the concept of faster-than-light neutrinos, and the proposed discovery of arsenic-based life forms. Each of these instances eroded credibility and served as a stark reminder of the imperative to rigorously validate findings before public disclosure. Nevertheless, delays inevitably breed suspicion. If Atlas, for instance, exhibits unusual spectral characteristics, something that deviates from established models of natural cometary behavior, researchers might opt to withhold that data until absolute certainty is achieved. The process of peer review typically spans several months, and subsequent revisions can extend this period further. By the time a scientific paper is published, the celestial conjunction might have passed. Atlas will have reappeared, and the narrative surrounding its appearance will have shifted. During this interim, speculation flourishes. The most dire interpretations are often assumed. The notion of deliberate cover-ups takes root. Are there valid justifications for withholding data that extend beyond scientific prudence? Conceivably, if Atlas were to display indications of artificial origin, if its spectral data contained discernible technosignatures, one could reasonably argue that prematurely disclosing such information could trigger widespread global upheaval. Governments might require time to conduct assessments, coordinate responses, and formulate official statements. International protocols already exist for managing potential contact with extraterrestrial intelligence, frameworks designed to guide the handling of such a monumental discovery. These protocols presuppose deliberate decision-making processes rather than hasty pronouncements driven by the pressures of social media. Conversely, astronomy is inherently a global endeavor. Atlas is being observed by telescopes located in numerous countries. Amateur astronomers are actively tracking its progress. Independent research teams are gathering their own sets of data. The act of suppressing information across such a widely distributed network is, in practical terms, nearly insurmountable. Someone somewhere would invariably leak the information. Leaks are an almost universal constant. The historical record of whistleblowing, both within scientific and governmental spheres, unequivocally demonstrates that secrets rarely remain confidential for extended periods. Therefore, what is the most probable reality? It is highly likely that no grand conspiracy is at play. What we are likely witnessing is the inherent complexity and occasional disarray that characterizes the scientific process. Data analysis requires time. Results must undergo validation. Scientific papers necessitate meticulous writing and rigorous review. Some information may indeed be delayed for legitimate reasons, such as scientific caution or the adherence to proprietary data periods. Other information might be subject to classification due to national security concerns, although it is improbable that this would encompass the majority of Atlas observations. And some of the circulating rumors are, in all likelihood, simply speculative conjecture masquerading as privileged insight. However, the current celestial conjunction presents a perfect storm for fostering suspicion. The object will become obscured from our view. Direct observation will be impossible. Whatever transpires during this period of invisibility will occur unobserved. When Atlas reemerges, our knowledge will be limited to what our instruments can detect and what researchers elect to share. If a discrepancy arises between the events that transpired and the information we are provided, we will possess no means of verification. The obscured phase of the conjunction transforms into an information blackout. In this context, citizen science assumes paramount importance. Independent observers, amateur astronomers equipped with backyard telescopes, serve as a vital check on institutional authority. They can collect data that bypasses official channels. They can disseminate their findings online without the protracted delays associated with peer review. They are not subject to the same institutional pressures or constraints as professional scientists. If any noteworthy events occur with Atlas following its reappearance, if the object appears altered or behaves in an unexpected manner, amateurs are likely to be the first to notice and report it. This distributed network of watchful eyes significantly impedes any attempts at information suppression. Furthermore, there is the pertinent question of what constitutes meaningful data in this specific scenario. If Atlas were to fragment during its obscured phase, and we were to observe these fragments upon its reappearance, that would constitute an observable, undeniable fact, exceptionally difficult to conceal. However, the interpretation, the underlying explanation for such fragmentation, is where control can be exerted. Was it a consequence of natural thermal stress, the gravitational pull of celestial bodies, or some other factor? The raw data may become publicly available, but the narrative surrounding it can be carefully curated. Historical precedents abound. The ongoing discourse surrounding unidentified aerial phenomena, commonly known as UFOs, has vividly illustrated how governmental reluctance to acknowledge observations can inadvertently fuel conspiracy theories. For decades, official policy was characterized by outright denial or outright dismissal. Then, abruptly, acknowledgement followed. Yes, we have indeed been tracking unexplained objects. Yes, some of them remain unidentified. The chasm between what was occurring and what was officially admitted created a persistent deficit of trust. A similar situation could unfold with interstellar objects. If institutions fail to maintain transparency, the question arises, can we truly trust what we will observe, or more accurately, what we will be told? Ideally, these two aspects should be congruent. Observations should be public. Data should be readily accessible. Interpretations should be subject to open debate. However, the reality is invariably more intricate. There are invariably intervals between the initial observation and its subsequent announcement. The critical question is whether these intervals represent innocent delays or deliberate obfuscation. In the case of Atlas, we will only be able to form a definitive judgment once the post-conjunction data becomes available, and we can juxtapose independent observations with official pronouncements. The debate surrounding data suppression is not intended to validate conspiracy theories. Rather, it aims to acknowledge that the flow of information within both scientific and governmental domains is not always a straightforward process. Various pressures, incentives, and constraints invariably influence what information is shared and when it is shared. Cultivating an awareness of these factors does not equate to paranoia. It signifies an informed perspective. And when confronted with a phenomenon as unprecedented as an interstellar object vanishing during its closest approach to the sun, being informed necessitates a commitment to questioning, to verifying, and to demanding transparency. The opaque phase of the conjunction is imminently closing. When it eventually reopens, we will gain insight into what lies within. However, whether we will witness the entirety of what transpired or merely what we are intended to see remains a question we must persistently pose. Part 8 delves into the Loeb factor. It is impossible to discuss interstellar objects and the intriguing possibility of artificial origins without referencing Avi Loeb. He has emerged as the prominent, albeit controversial, proponent of the "what if it's a probe" hypothesis, and his involvement with the celestial object Atlas further intensifies an already compelling narrative. So, who exactly is Avi Loeb? What is his central argument, and why does it carry significant weight? Avi Loeb holds the distinguished position of a professor of astrophysics at Harvard University, having previously served as the chairman of its astronomy department. His prolific academic career includes the publication of hundreds of research papers on subjects ranging from black holes and cosmology to high-energy astrophysics. By any objective standard, he is an accomplished scientist with an impeccable academic record. He is not a figure relegated to the fringes, nor is he an individual easily dismissed. It is precisely this stature that lends such provocative weight to his perspectives on interstellar objects. Professor Loeb first garnered widespread public attention through his meticulous analysis of Oumuamua, the inaugural confirmed interstellar object detected in 2017. Oumuamua presented a peculiar profile. It possessed an elongated shape, exhibited a tumbling motion, and displayed a subtle acceleration that could not be accounted for by gravitational forces alone. The prevailing scientific consensus attributed this anomalous acceleration to outgassing, the standard explanation for the aberrant behavior of comets. However, Loeb proposed an alternative. Could Oumuamua have been a solar sail, a delicate reflective sheet propelled by the pressure of solar radiation, possibly of artificial origin? This suggestion sent ripples through the scientific community, eliciting considerable skepticism. The overwhelming majority of astronomers favored natural explanations, deeming them far more plausible than the invocation of extraterrestrial technology. Undeterred, Loeb maintained his position. He was not asserting with definitive certainty that Oumuamua was artificial. Rather, he was arguing that the hypothesis of an artificial origin should not be summarily disregarded without thorough investigation. While it is true that extraordinary claims necessitate extraordinary evidence, it is equally true that extraordinary dismissals require extraordinary justification. If we refrain from investigating, we can never discover. Loeb has now turned his scholarly attention to Atlas. In a preliminary research paper, he highlights the remarkably coincidental timing of Atlas's solar conjunction and perihelion. The conjunction is scheduled for October 21st, while its perihelion, the point of closest approach to the Sun, is set for October 29th, an interval of just 8 days. He further notes the object's alignment with the ecliptic plane, its trajectory passing in proximity to several planets, while remaining obscured from view, and a temporal confluence that maximizes energy potential while minimizing observational opportunities. He stops short of claiming Atlas is artificial. Instead, he asserts that it warrants serious consideration, that its characteristics are extraordinary, and that the question of whether its circumstances are coincidental or indicative of deliberate design is one worthy of earnest inquiry. His detractors, who are numerous, contend that his approach constitutes sensationalism. They argue that by even cautiously raising the possibility of artificial origin, Loeb inadvertently lends an unwarranted air of credibility to speculation that lacks any empirical foundation, effectively conflating the unusual with the artificial, a logical leap unsupported by the available data. They point out that the cosmos is replete with unusual phenomena. Rare events occur. Low probability outcomes are statistically inevitable given a sufficient number of trials. The fact that Atlas's temporal positioning is peculiar does not inherently imply engineered circumstances. Loeb's rejoinder is rooted in philosophical principles. He contends that scientific progress thrives on the exploration of possibilities, not their premature dismissal. He posits that the burden of proof operates reciprocally. If one advocates for a natural explanation, a convincing account should be provided. When natural explanations become strained, necessitating the invocation of multiple improbable factors, alternative hypotheses deserve consideration, not necessarily immediate acceptance, but certainly earnest consideration. So, what specific data points does Loeb highlight? The perihelion distance of 1.36 astronomical units places Atlas within a region where solar heating is significant, though not to a catastrophic degree. It is sufficiently close to potentially activate cometary processes, but not so close as to induce its destruction. The timing of perihelion, occurring 8 days after solar conjunction, signifies that the object reaches its peak velocity and energy while being completely invisible from Earth. If one were orchestrating a maneuver, a trajectory adjustment, or the deployment of instruments, this precise moment would represent the ideal opportunity. Maximum energy generation via the Earth effect, coupled with maximum concealment from terrestrial observation. He also draws attention to the object's planetary encounters. While concealed behind the Sun, Atlas's trajectory brings it into relatively close proximity with Mars, Venus, and Jupiter. These are not direct collisions, but they fall within the observational range if the object were equipped with instruments capable of data acquisition. This is not conclusive proof of anything. Natural comets frequently traverse near planets. However, the pattern of planetary proximity during a period of invisibility adds another layer to a collection of factors that, while individually explainable, collectively generate a sense of curiosity. Professor Loeb has established the Galileo Project, an initiative dedicated to the search for evidence of extraterrestrial technological artifacts. This project employs sophisticated telescopes and sensors to monitor the night sky for anomalies that could potentially indicate the presence of artificial objects. Atlas aligns with the profile of an object that the Galileo Project would undertake to investigate, not due to any pre-existing proof of artificiality, but rather because its unusual characteristics warrant rigorous scrutiny. If our pursuit of techno-signatures is to be taken seriously, we cannot afford to disregard potential candidates simply because they might ultimately prove to be natural phenomena. Why then do mainstream astronomers exhibit resistance to Loeb's analytical framework? Several compelling reasons contribute to this. Firstly, the matter of prior probability. The statistical likelihood that any given interstellar object is artificial is exceedingly remote. Interstellar travel represents an immense undertaking, demanding extraordinary energy expenditures. The number of civilizations capable of constructing such probes, if any even exist, remains entirely unknown. Placing one's confidence in an artificial origin without unequivocal evidence is akin to wagering against overwhelming odds. Secondly, the risk to professional reputation. The field of astronomy has been historically cautious, having been once misled by premature claims. Pulsars were briefly and erroneously referred to as LGM signals, little green men, before their true nature as neutron stars was elucidated. The iconic face on Mars was later revealed to be an artifact of light and shadow. A pattern of unsubstantiated pronouncements regarding alien origins can significantly erode scientific credibility. Thirdly, there is a pervasive concern that an excessive focus on artificial explanations serves as a distraction from fundamental scientific inquiry. The study of Atlas as a purely natural object offers valuable insights into interstellar chemistry, orbital dynamics, and the complex processes of cometary activity. Reframing it as a potential probe diverts attention towards speculative avenues that may prove unproductive. Both time and resources are finite commodities. Should they be allocated to pursuing improbable long shots or to diligently investigating phenomena that are already known to exist? Loeb's counterargument is that these pursuits are not mutually exclusive. He suggests that investigating the possibility of artificial origins does not preclude the continuation of naturalistic research. Furthermore, he posits that by rigorously disproving the artificial hypothesis, we paradoxically enhance our understanding of natural phenomena. Conversely, he argues, if we consistently dismiss the possibility out of hand, we forfeit any chance of detecting it should it indeed be present. The inherent tension lies at the very core of how science approaches ambiguous cases. Do we follow the data relentlessly, irrespective of where it leads, even into uncharted and potentially uncomfortable territory? Or do we apply Occam's razor with unwavering severity, prioritizing the most parsimonious explanation until compelling evidence mandates its abandonment? Both methodologies possess inherent value and have historically yielded significant breakthroughs. The fundamental question remains: which approach is most applicable to the enigma of Atlas? Consequently, what is the implication of the Loeb factor within the broader narrative? It signifies that the hypothesis of artificial origin remains a viable, albeit debated, consideration within public discourse. It means that when Atlas reappears, observers will be keenly anticipating not only signs of natural activity, but also indicators of something more profound: deviations in trajectory, unexpected fragmentation, discernible signals, anything that departs from the established characteristics of a cometary body. Professor Loeb has effectively established a framework for heightened scrutiny. Regardless of whether one aligns with his investigative methodology, this heightened scrutiny will invariably shape our perception and interpretation of future observations. If Loeb is even partially correct, if there exists a minuscule 1% probability that Atlas represents something other than a natural comet, then the period of obscuration during conjunction becomes the most critical juncture of the entire event. It is during this phase that developments might occur that elude our observational capabilities. It is the phase during which any reveal, if one is destined to occur, will transpire away from the public eye. And if he is ultimately proven wrong, if Atlas conforms entirely to conventional scientific expectations, a natural interstellar comet governed solely by the laws of physics, then this entire discourse will be remembered as an intriguing intellectual detour, a speculative what if that ultimately failed to materialize. Regardless of the eventual outcome, however, the Loeb factor has ensured that our collective attention is firmly fixed on this celestial enigma. And in the realm of scientific exploration, focused attention is invariably the indispensable precursor to discovery. Part 9 addresses the energy puzzle, specifically focusing on why energetic considerations are paramount when contemplating spacecraft maneuvers. This inquiry necessitates an understanding of a concept from orbital mechanics known as the Orth effect. Grasping this principle is key to comprehending the profound significance of Atlas's precise temporal positioning. The Orth effect, named in honor of Hermann Orth, a foundational figure in rocketry, operates on a principle that is both elegantly simple and remarkably profound. A rocket's thrust, when applied at high velocity, results in a greater augmentation of kinetic energy than the same thrust applied at a lower velocity. To articulate this differently, if the objective is to modify one's trajectory with the utmost efficiency, such an alteration should be undertaken when one is moving at the greatest possible speed. For Atlas, that pivotal moment is perihelion, scheduled for October 29th, when the object achieves its closest proximity to the Sun and consequently attains its maximum velocity. Let us examine the underlying mathematics in straightforward terms. Kinetic energy is defined by the equation 1/2 mass multiplied by velocity squared. The squared term is critically important. If an object is traveling at 10 kilometers per second and its velocity is increased by 1 kilometer per second through a propulsive burn, its kinetic energy will increase proportionally to the square of its final velocity minus the square of its initial velocity. However, if the object is already traveling at 50 kilometers per second and receives the same 1 kilometer per second impulse, the resulting energy change will be substantially larger due to the influence of that squared factor. In essence, greater velocity yields a more significant energetic return for the effort expended. For comets and asteroids, this phenomenon typically holds little relevance. They do not engage in propulsive burns. They simply traverse gravitational fields, acting as passive entities adhering to Newtonian physics. But if Atlas were an artificial construct possessing any inherent capability to alter its trajectory, perihelion would represent the optimal juncture for such an action. A minor impulse applied at perihelion could instigate a substantial modification in orbital energy, thereby enabling significant trajectory adjustments with a remarkably minimal expenditure of fuel. This principle is precisely what spacecraft engineers leverage for gravitational assists and various orbital maneuvers. Now, let us integrate the factor of solar conjunction. Atlas reaches perihelion a mere 8 days after entering solar conjunction, meaning it achieves the peak energetic moment of its trajectory while remaining entirely imperceptible to terrestrial telescopes. If the intent were to execute a maneuver stealthily, one could scarcely devise a more opportune temporal alignment. Maximum energetic enhancement coincides with maximum observational privacy. The circumstances appear almost too perfectly orchestrated. Natural processes can also manifest energetic releases at perihelion. This is the conventional scientific explanation for any observed anomalies. As comets approach the sun, they experience intensified heating. Subsurface ices vaporize, leading to pressure buildup and subsequent eruptions of gas and dust from the nucleus, effectively functioning like minuscule rocket engines. This outgassing process is responsible for the characteristic cometary tail and can induce measurable alterations in trajectory. We observe this phenomenon routinely. It is considered a normal occurrence. However, the magnitude and timing of these events are crucial considerations. If Atlas exhibits substantial outgassing precisely at perihelion, that would be an expected behavior. If it releases fragments, that too is within the realm of typical cometary activity. Comets are inherently fragile bodies, susceptible to fracturing under thermal stress. The gravitational tidal forces exerted by the sun can also lead to their disintegration. None of these processes inherently necessitate artificial intervention. But if Atlas were to engage in behavior that is energetically improbable, exhibiting energy expenditure that exceeds what natural outgassing could plausibly provide, that is when significant questions would inevitably arise. We must also consider the context of solar energy availability. At a distance of 1.36 astronomical units from the Sun, Atlas receives approximately half the solar illumination that Earth does. This is still a considerable amount of energy. If the object possesses any capacity for solar energy collection, perhaps through photovoltaic or thermal systems, perihelion would represent the period of maximum available power. While this remains purely speculative, the convergence of high velocity, intense solar flux, and a state of observational invisibility creates a unique window of opportunity wherein a multitude of scenarios become plausible. Let us contemplate the potential outcomes of a trajectory modification at perihelion. If Atlas were to undergo a significant deceleration or acceleration, it could fundamentally alter its subsequent trajectory upon exiting the solar system. Natural comets typically depart on hyperbolic orbits that bear a strong resemblance to their ingress trajectories, albeit with slight deflections caused by the sun's gravitational influence. However, a deliberate propulsive burn could effect a more profound change. The object could be directed toward an entirely different destination, perhaps another star system along its path. Alternatively, it could release smaller probes, each set on divergent trajectories, potentially heading toward disparate celestial targets. The energy available at perihelion renders such maneuvers feasible in ways that would be impossible at other points in its orbital path. The observational implications would be readily apparent, assuming we possess the capability to observe these events. A sudden increase in luminosity would clearly indicate the release of energy. Altering the tail's physical form would reveal different patterns of gas release. Any pieces breaking away from the main structure would be seen as distinct points of light. Changes in its path would be evident in measurements of its celestial position. However, all these indicators necessitate observation, precisely what is impossible during conjunction. This creates an imbalance. Both natural and artificial explanations predict activity around the point of closest approach to the sun. The divergence lies in the specifics, the intensity and distinctiveness of this activity. Without the ability to observe, differentiation becomes impossible. We are left to infer past events from before and after snapshots, a method inherently fraught with uncertainty. The debate between natural versus manufactured explanations boils down to probability and simplicity. Natural processes are well understood. We have examined countless comets, comprehending their thermal evolution and outgassing behaviors. We acknowledge that unusual occurrences happen, but they are explainable within the framework of physics. Manufactured explanations, conversely, require postulating technologies beyond our current experience, civilizations we have not encountered, and capabilities we can only envision. Occam's razor suggests favoring the most straightforward explanation. Yet this principle is a guideline, not a fundamental law. Sometimes the simpler answer proves incorrect. What would definitively prove an artificial origin? Direct detection of technology, a radio signal, a visible construct incompatible with natural formation, or trajectory alterations that defy the laws of momentum unless accounted for by specific mass expulsions. Chemical signatures indicative of industrial processes would serve as conclusive evidence. However, all these require observation, and observation is precisely what is denied during the crucial period. Consequently, the energy enigma persists. We understand that perihelion is when energy conditions are most conducive to activity, whether natural or artificial. We recognize the timing coincides with conjunction, the period of maximum obscurity. We know that if any significant event is to occur, it will be then. But we will not witness it. We will only see the aftermath. And interpreting results without understanding the process inherently leads to ambiguity. The celestial body is now accelerating rapidly, plummeting towards the sun. Within days, it will reach its zenith velocity, peak heat, maximum energy, and ultimate invisibility. Whatever Atlas is destined to do, whatever its potential capabilities, the critical moment approaches, and we are poised to miss it. Part 10. Serendipity or Design. Let us pause and consider the complete panorama, all the contributing factors we have examined, and pose a direct question. Are we observing mere chance or deliberate orchestration? How many unusual concurrences can accumulate before probability becomes untenable? Let us begin with the trajectory. 3 Atlas enters our solar system with an alignment close to the ecliptic plane, within approximately 5 degrees. Most interstellar objects are expected to arrive from random angles. This alignment with the ecliptic is unusual but not entirely improbable. A generous estimate for the probability of an ecliptic alignment might be 10%. This is noteworthy but still within the bounds of chance. Now let us incorporate the timing. Conjunction is scheduled for October 21st, with perihelion on October 29th, an 8-day interval. The object's closest approach will occur when it is hidden from Earth's view. How frequently does this occur? For visitors from other star systems, we lack statistical data. Prior to Atlas, we had identified only 2 such objects, neither exhibiting this behavior. However, for comets originating within our solar system, experiencing conjunction during perihelion is uncommon, perhaps occurring in only 1 out of 50 instances. This introduces another factor of 2%. Now, consider the direction. Atlas is approaching from the general vicinity of Sagittarius towards the galactic center. Oumuamua's trajectory and the WOW signal originated from similar directions. Sagittarius encompasses roughly 5% of the sky, adding another factor of 5%. Finally, let us include the planetary encounters. While concealed, Atlas passes within observable proximity of Mars, Venus, and Jupiter. These are not close flybys, but their trajectories place the object in positions where a probe equipped with instruments could gather data. What is the probability of such a path occurring randomly? Precise calculation is difficult, but let us assign a 10% chance. Multiplying these probabilities, assuming independence, 0.1 multiplied by 0.02 multiplied by 0.05 multiplied by 0.1 equals 0.0001, or 1 in 100,000. This is not impossible. Unlikely events do transpire. However, it begins to strain credulity. Now, let us add the velocity anomalies, minor deviations from purely gravitational predictions, potentially attributable to outgassing, but not definitively proven. Let us also include the unconfirmed and unpublished rumored spectroscopic anomalies. Furthermore, consider that all this unfolds during a period of heightened solar activity, coinciding with a meteor shower and a dual comet display in the night sky. While each of these factors in isolation can be explained naturally, their convergence forms a pattern that is increasingly difficult to disregard. Here lies the counterargument. Humans are inherently predisposed to recognizing patterns. We perceive faces in clouds and conspiracies in coincidences. Cognitive biases, such as confirmation bias and the clustering illusion, lead us to overemphasize unusual alignments while underestimating base rates. When examining vast amounts of data, patterns will inevitably emerge. Some will possess significance, while the majority will be mere statistical noise. The challenge lies in discerning which is which. The naturalist perspective posits that Atlas represents noise, an interstellar comet with an unusual orbit and unfortunate timing, nothing more. The universe is vast and random events tend to cluster. We are witnessing one such cluster and mistaking it for intentional design. Given a sufficient number of interstellar objects over an extended period, one is statistically bound to exhibit all these aligned factors purely by chance. Atlas, in this view, is simply that singular instance. The choreography perspective argues that the alignment is too precise, too convenient. It contends that repeatedly invoking chance for each individual factor ultimately becomes less parsimonious than postulating intent. It suggests that if something appears designed, behaves as if designed, and adheres to patterns consistent with design, then perhaps it is indeed designed, not proven, but plausible enough to warrant serious investigation. There is a philosophical dimension to this debate. Are we participants in a cosmic dialogue we do not yet comprehend? This concept is not novel. Carl Sagan explored it in Contact, and Arthur C. Clarke in Rendezvous with Rama. The notion is that intelligence might communicate not through radio waves, but through physical objects, artifacts, or probes that traverse interstellar distances, carrying information. If such a system exists, a galactic communication network, we would anticipate encountering objects with anomalous trajectories, peculiar timing, and patterns that hint at deliberate intent. However, expectation does not equate to evidence, and science fiction remains distinct from scientific fact. The onus of proof rests squarely on those asserting extraordinary claims. Presently, we lack that definitive proof. We possess suggestive data, intriguing coincidences, and a considerable amount of conjecture. We must also consider the concept of mirror symmetry. Our own Voyager probes are venturing outward, carrying golden records that encapsulate information about humanity. Voyager 2, for instance, is heading roughly towards the constellation Telescopium, though its trajectory will eventually curve due to galactic dynamics. Over millions of years, it might traverse regions near Sagittarius. If another civilization were to discover Voyager, they would encounter an artificial object on an interstellar trajectory, its path shaped by both gravity and intelligent design. Are we witnessing the cosmic equivalent? Perhaps someone else's Voyager, inbound rather than outbound, traversing a corridor that brings it through our celestial neighborhood. It is a poetic notion. The cosmos as a venue for exchange, where civilizations dispatch emissaries in the form of probes, knowing they will arrive long after their creators have ceased to exist. They are akin to messages in bottles cast into the galactic ocean. Some arrive, most do not. But those that do carry narratives, data, and evidence of other worlds. Yet, poetry, too, is not proof. The universe operates according to the immutable laws of physics, not metaphorical interpretations. If Atlas is a probe, it is a probe because it was constructed as such, not because we wish it to be. And if it is a comet, it remains a comet irrespective of our desires to the contrary. So, where does this leave us? Suspended between coincidence and choreography, unable to definitively prove either, we await Atlas's reappearance to furnish us with more data. The object itself remains indifferent to our debate, pursuing its trajectory, whether natural or engineered, unconcerned by our speculation. However, we are invested. We must be. For if there exists even a remote possibility that the observed pattern is genuine, that the choreography is real, then failing to recognize it would constitute the most profound oversight in human history. The conjunction window is rapidly closing. The object is about to slip behind the sun, leaving us with our questions, our doubts, and our hopes. When Atlas emerges once more, when we can once again observe it, will the pattern resolve into clarity? Or will it remain ambiguous, forever balanced between conflicting interpretations, a cosmic Rorschach test reflecting our own assumptions back at us? Coincidence or choreography? The answer may already be inscribed within its trajectory. We simply await its reappearance to decipher it. Part 11. Quantum Communication Advancements. While we await 3 Atlases' reemergence from behind the sun, let us consider developments occurring in October 2025 that could fundamentally alter our understanding of interstellar communication. Humanity is on the cusp of deploying operational quantum communication networks. This advancement holds significant implications for how we search for, and potentially overlook, signals from other civilizations. In October 2025, the European Space Agency and the Chinese space programs have reported successful satellite-based quantum entanglement experiments spanning continental distances. These are no longer confined to laboratory demonstrations. They represent functional systems transmitting secure information via entangled photon pairs. This principle is rooted in quantum mechanics, specifically the phenomenon where 2 particles become correlated in such a way that measuring one instantaneously influences the other, irrespective of the distance separating them. It is important to clarify that quantum entanglement does not facilitate faster-than-light communication in the conventional sense. One cannot transmit a message instantaneously across space by measuring entangled particles. The no-communication theorem in quantum mechanics prohibits this. However, what can be achieved is the creation of communication channels that are inherently secure and impervious to classical interception, as any attempt to interfere with the signal inevitably disrupts the quantum state. For the purpose of secure communication, quantum networks represent a revolutionary leap. However, here lies the crucial connection to interstellar objects. For the past 70 years, our endeavors to detect extraterrestrial intelligence have been overwhelmingly focused on radio signals. We direct radio telescopes towards the heavens, listening for narrow-band transmissions, patterns that could not possibly arise from natural phenomena. We operate under the assumption that advanced civilizations, either intentionally or inadvertently, broadcast signals, and that we can detect these transmissions if we search diligently enough. This assumption underpins every search for extraterrestrial intelligence program ever funded. But what if this assumption is flawed? What if radio represents a transient phase, a technological adolescence from which civilizations eventually mature? Humans utilized radio for barely a century before developing alternative communication methods, such as fiber optics, laser communication, and now quantum networks. If this evolutionary progression is widespread, if civilizations naturally transition from broadcast radio to directed laser signals and subsequently to quantum entanglement, then our current search methods may be targeting an obsolete form of communication. We are, in essence, searching for smoke signals in an era of encrypted quantum channels. Imagine an advanced civilization, millennia or even millions of years beyond our current technological stage. Would they still rely on radio? It is highly improbable. Radio is inefficient, broadcasts indiscriminately in all directions, and inadvertently leaks information to any entity that might be listening. A mature civilization would likely employ tightly focused laser beams for point-to-point communication, minimizing energy expenditure and maximizing security. Eventually, they would likely migrate to quantum networks, offering unparalleled security and potentially harnessing principles of physics yet undiscovered by us. If such networks exist, if there is a cosmic quantum internet connecting civilizations, we would be effectively invisible to it. Our radio telescopes are incapable of detecting quantum entanglement, and we lack the fundamental understanding of what to even search for. It would be akin to attempting to access the internet using a telegraph. The infrastructure might exist and data might be flowing, but we would be employing technology from a bygone era, rendering us unable to interface with the contemporary system. This has direct relevance to the Atlas object. If it is an artificial construct, a probe dispatched by a civilization possessing advanced technology, it might not communicate through methods detectable by us. It might not broadcast radio signals. It could potentially connect to a quantum network during perihelion, transmitting data that we cannot intercept and receiving instructions that we cannot observe. And given that this would occur during conjunction, a period of our blindness, we would remain unaware that it had transpired. This is not merely speculative conjecture. It is an extrapolation derived from our own technological trajectory. If we are on the verge of deploying quantum communication satellites in 2025, a civilization only a few centuries more advanced would possess fully developed quantum networks. For a civilization millions of years ahead, their communication methods are beyond our current comprehension. They might utilize gravitational waves, manipulate space-time directly, or harness principles of physics we have yet to uncover. The historical context is crucial. 50 years ago, we operated under the assumption that radio represented the universal medium for communication. Electromagnetic radiation, traveling at the speed of light, easily generated and detected, and thus a logical choice for any technological civilization. However, our certainty has waned. Radio may represent merely a developmental stage, a phase that civilizations pass through before adopting more sophisticated methodologies. If this is the case, then decades of SETI efforts focused on listening may have been directed at the wrong frequency, both literally and figuratively. Does this render SETI efforts futile? Not necessarily. Nascent civilizations, akin to our own, would likely still employ radio. We might detect their transmissions during their radio loud phase. However, more advanced civilizations, those capable of constructing interstellar probes, might be radio silent. Detecting them would necessitate alternative approaches: optical SETI, searching for laser pulses; infrared surveys, looking for waste heat emitted by megastructures; gravitational wave monitoring; and the search for technosignatures, focusing on atmospheric pollution or industrial byproducts present in exoplanet spectra. Alternatively, we could focus on detecting the probes themselves: physical artifacts traversing space, interstellar objects exhibiting unusual trajectories, such as Atlas. If civilizations do not broadcast but instead dispatch emissaries, probes carrying information physically, then detecting these probes becomes our most promising avenue for establishing contact. And if we are not vigilant, if we dismiss unusual objects as natural phenomena without thorough investigation, we risk missing the message entirely. The quantum communication breakthrough announced in October 2025 serves as a potent reminder that technology is in constant evolution. What appears cutting-edge today will likely be obsolete within decades. What seems impossible now may become commonplace in centuries. If our objective is to detect signals, we must continuously refine our assumptions, always questioning what might be eluding us, what methods we have yet to consider, and what channels remain unmonitored. For Atlas, this implies that the absence of a radio signal does not equate to the absence of communication. The object could be transmitting information through means undetectable to us. It could be receiving in ways we cannot jam, or it could be an integral part of a network whose existence we are unaware of. Furthermore, the conjunction window, that period of obscured visibility, might be precisely when it engages with such a network, uploads data, downloads instructions, or executes whatever its designated mission entails. Conversely, it could simply be a celestial body, a comet, or a fragment of interstellar debris devoid of any intelligence beyond that of an inanimate object. We simply do not know. However, the possibility that we are tuned to the wrong frequency, that we are missing signals all around us due to the use of outdated methods, should instill in us humility, curiosity, and a perpetual questioning of whether we are truly perceiving the complete picture. The quantum revolution is upon us. It is plausible that the universe experienced its own quantum revolution millions of years ago, and we are only now catching up, blinking in the unfamiliar light of technologies we barely grasp, and wondering what else may have passed us by unnoticed. Part 12. Artificial Intelligence and Cosmic Data. In October 2025, another significant advancement is quietly transforming the field of astronomy. A novel machine learning system, the specific details of which are still emerging, has been applied to archival gravitational wave data and SETI datasets, resulting in the identification of 14 previously undetected events over the past decade. These represent 14 signals or patterns that eluded human analysts, 14 elusive entities that were always present in the vast data, but remained invisible until artificial intelligence brought them to light. This development is crucial because astronomy is currently inundated with data. Every night, survey telescopes capture terabytes of imagery. Every second, gravitational wave detectors record minute strain measurements. Every hour, radio telescopes gather spectral data from thousands of celestial sources. Human astronomers simply cannot process this overwhelming volume. Consequently, we employ filtering mechanisms, prioritizing what appears most promising and disregarding the remainder. In this process, inevitably, we overlook certain phenomena. Machine learning fundamentally alters this paradigm. Algorithms possess the capacity to process millions of data points concurrently. They do not experience fatigue and are devoid of biases regarding what constitutes interesting data. They discern patterns that human observers miss, identify correlations obscured by noise, and detect anomalies that subtly contravene expectations. The 14 detections reported in October serve as irrefutable evidence that we have been missing signals all along, not due to their absence, but due to our insufficient analytical methods. Applying this principle to 3 Atlas, observatories are currently accumulating final measurements prior to the conjunction period. This includes images, spectral analyses, and astrometric data. This information is subsequently stored in archives. Human astronomers examine this data, extract the most apparent features, and publish findings regarding composition and trajectory, the standard procedure. However, what if there are subtle patterns within this data that are imperceptible to human observers? These could include minute periodicities in brightness, unusual correlations between spectral lines, or trajectory deviations that, while individually within acceptable error margins, collectively hold significant meaning. An artificial intelligence system trained on the behavior of comets might flag Atlas as anomalous, even if human analysts do not. The true power of AI becomes apparent post-conjunction. As Atlas reemerges, new observations will be gathered. Comparing these pre- and post-conjunction data requires meticulous analysis. Did the object fragment? Did its brightness alter? Did its trajectory shift? Human astronomers will undertake this task, but their focus will likely be on obvious discrepancies, substantial changes, and clear signatures. AI, however, can delve deeper. It can detect a 3% variation in brightness that might indicate surface modifications. It can identify trajectory shifts measurable in meters per second. It can compare spectral fingerprints and discern that a specific emission line ratio has changed by an amount that is statistically significant, yet visually imperceptible. This phenomenon has already been observed in other scientific domains. The detection of exoplanets was revolutionized by machine learning algorithms that identified planetary transits within Kepler telescope data that human analysts had previously classified as noise. Gravitational wave astronomy employs AI to differentiate genuine events from instrumental artifacts. The detection of fast radio bursts relies on algorithms that automatically sift through vast quantities of radio data. In each of these instances, AI has not replaced human astronomers, but has instead augmented their capabilities, uncovering phenomena that humans would have missed, thereby enabling humans to conduct follow-up investigations and confirm findings. For interstellar objects, AI has the potential to be transformative. We have confirmed the existence of only 3 such objects: Oumuamua, Borisov, and now Atlas. However, how many have we overlooked? How many objects might have traversed the inner solar system with unusual trajectories that went undetected because they were faint, moved too rapidly, or appeared in data that was not subjected to rigorous scrutiny? Applying AI retroactively to decades of archival sky survey data could potentially reveal a dozen or more interstellar visitors that have been hiding in plain sight. Furthermore, there is the inherent challenge of potential AI hallucinations. Neural networks are occasionally prone to identifying patterns that do not exist in reality, either as artifacts of their training data or as quirks of their algorithms. A false positive is a more detrimental outcome than a missed detection, as it leads to wasted resources pursuing illusory phenomena. Therefore, AI-generated results necessitate validation. Human oversight is essential to verify that detected patterns withstand rigorous examination. This process, while potentially time-consuming, ensures the reliability of the findings. Consider this hypothetical scenario. Atlas reappears from behind the sun in late November. Observational posts gather information. Initial human interpretation reveals nothing out of the ordinary. The celestial body resembles a comet, behaves like one, and aligns with prior theoretical estimations. The case is closed. It's a natural occurrence. However, an advancement occurs when a computational system processes the gathered information through an artificial intelligence framework designed for anomaly identification. The program flags a peculiarity. There's a recurring pattern in the luminosity fluctuations that doesn't correspond to the object's rotation. A subtle alteration in its path suggests a minor propulsive force. A spectral anomaly emerges post-conjunction that was absent previously. Individually, these are minor points of contention, yet the AI confidently asserts the significance of the combined indicators. Do we proceed with an investigation? Do we place faith in the AI's assessment? Or do we dismiss it as a false positive, mere computational static unworthy of pursuit? This represents the cutting edge of astronomical exploration, where we rely on automated systems to direct human inquiry. It involves harmonizing algorithmic insights with human discernment. Success in this endeavor could herald an extraordinary discovery. Failure might mean overlooking a significant finding or expending resources on phantom phenomena. We also face the challenge of massive data volumes. The search for interstellar objects necessitates continuous observation of the entire celestial sphere, tracking countless points of light, calculating their trajectories, and identifying hyperbolic orbits. This scale is beyond human capacity. We depend on automated mechanisms, and these mechanisms, in turn, rely on sophisticated algorithms. If these algorithms lack the necessary refinement, if they inadvertently filter out objects that move too rapidly or appear too faint, we risk missing visitors from beyond our solar system. Enhancing these algorithms with contemporary artificial intelligence methodologies could dramatically improve detection rates. The Vera C. Rubin Observatory, previously designated LSST, is slated for imminent activation. It will meticulously scan the entire observable sky at brief intervals, generating an unparalleled torrent of data. Projections indicate it will identify dozens of interstellar objects annually once operating at its full operational capacity. This hinges entirely on the data processing pipeline's ability to manage the immense volume. The AI system's capacity for near real-time candidate identification and the swift follow-up actions by human observers before these objects diminish in visibility or move beyond observational range. The success of interstellar object research in the coming decade is profoundly contingent on machine learning advancements. Specifically concerning Atlas, there's a possibility that concealed information will only be revealed through AI analysis. Perhaps the object left a subtle imprint in its pre-conjunction data, a clue to its behavior during its closest approach to the Sun. This imprint might be imperceptible to human senses, but readily apparent to a trained neural network. If so, this discovery will remain elusive unless someone conceives of performing the analysis. If no such analysis is conducted, the information will stay buried, locked away in archives, awaiting a pertinent inquiry. This brings us to a fundamental question concerning the search for extraterrestrial intelligence. We operate under the assumption that we will recognize a signal when it appears. But what if these signals are structured in a manner optimized for machine comprehension rather than human interpretation? What if advanced civilizations employ modulation schemes or error correction protocols that appear as mere noise to us, but are clearly decipherable by a sufficiently advanced AI? It is conceivable that we are currently immersed in alien transmissions, yet unable to acknowledge them due to our reliance on human intuition over machine-driven analysis. The same logic applies to physical constructs. If Atlas is indeed a probe, its design might incorporate features that are readily identifiable by algorithms but ambiguous to visual inspection. This could include surface markings, trajectory optimizations, or spectral characteristics that an AI trained on spacecraft engineering would instantly flag, while human astronomers might dismiss them as natural variations. We may require artificial intelligence to identify artificial entities. Therefore, the crucial question arises: are we prepared to allow artificial intelligence to guide our exploration? Are we comfortable trusting algorithmic conclusions, particularly when they diverge from our innate perceptions? Can we develop systems that effectively balance machine efficiency with human judgment? These are not merely technical considerations, but profound philosophical inquiries that touch upon the very essence of discovery, comprehension, and knowledge. Atlas is currently obscured, traversing its invisible phase. Upon its reappearance, human observation will be directed towards it, but so too will the analytical capabilities of artificial intelligence. Neural networks trained on vast quantities of astronomical data will be poised to detect patterns beyond our immediate perception. Which observational approach will yield clearer insights? Which might overlook the obvious? Which could generate phantom detections? The answers will soon become apparent. Crucially, the outcome of this investigation may determine whether we recognize one of history's most significant discoveries or dismiss it as insignificant data within a database. Part 13. Warnings of Solar Activity. October of 2025 portends more than just interstellar visitors and breakthroughs in quantum physics. The Sun itself is exhibiting increased volatility. The National Oceanic and Atmospheric Administration has issued advisories regarding the most intense cycle of coronal mass ejections observed since 2012. Solar storms are escalating in intensity, and space weather conditions are becoming increasingly turbulent. The timing of these events, much like other occurrences this month, is uncomfortably synchronistic. Coronal mass ejections are colossal expulsions of plasma and magnetic fields originating from the sun's corona. When directed towards Earth, they possess the potential to cause widespread disruption. The charged particles collide with Earth's magnetosphere, compressing it, inducing electrical currents in power grids, compromising satellite functionality, and interfering with radio communications. These events also generate spectacular auroras, the northern and southern lights, as particles interact with atmospheric gases along magnetic field lines. We are currently within the ascending phase of solar cycle 25. The sun's activity follows an approximately 11-year cycle characterized by fluctuations in magnetic complexity. Solar maximum, the peak of this activity, is fast approaching, signifying an increase in sunspots, solar flares, and coronal mass ejections. October of 2025 falls precisely within this heightened period of activity. Recent observations confirm the presence of several substantial active regions on the sun's surface, capable of producing significant eruptions. The irony in this situation is that as 3I Atlas recedes behind the sun's own activity may impede our observation of all other phenomena. Solar storms degrade the performance of telescopes, create ionospheric disturbances that impact radio astronomy, damage satellite instruments, and necessitate spacecraft entering safe modes. Essentially, the sun's position is not only concealing Atlas, but also obscuring our other observational instruments, creating a dual blackout. Furthermore, there is the question of whether solar activity might directly impact Atlas. The object is projected to pass within approximately 23 million kilometers of the sun at its closest approach. This proximity places it well within the sun's extended atmosphere, the heliosphere, where solar wind and magnetic fields exert considerable influence. At such distances, comets typically experience the solar wind, a continuous outflow of charged particles from the sun, traveling at hundreds of kilometers per second. This wind is responsible for pushing cometary tails away from the sun, creating their characteristic appearance. Coronal mass ejections, however, are distinct. They are transient, powerful bursts of plasma that travel at speeds exceeding the normal solar wind. Should a coronal mass ejection intersect Atlas's trajectory during its perihelion, the object could experience a sudden surge in particle density and magnetic field intensity. For a natural comet, this might trigger enhanced outgassing or tail activity. The effect on an artificial object remains unknown. It could be negligible or, conversely, detectable. The inability to observe prevents us from knowing. Solar storms also present challenges for spacecraft that might monitor Atlas during its conjunction phase. The Solar and Heliospheric Observatory, SOHO, maintains an orbit around the Sun-Earth L1 Lagrange point, positioned between the Sun and Earth. Its primary function is to monitor solar activity, making it somewhat resistant to radiation, but extreme storms can still affect its instruments. The Parker Solar Probe travels closer to the Sun than any spacecraft previously has, currently on a trajectory that will eventually bring it within approximately 6 million kilometers of the solar surface. While exceptionally radiation-hardy, even Parker has its limitations. If solar activity surges during Atlas's passage, observational data from these spacecraft could be compromised. The Solar Terrestrial Relations Observatory, STEREO, consists of 2 spacecraft orbiting the Sun at distinct positions, offering stereoscopic views of solar phenomena. STEREO could potentially capture Atlas from an angle not obscured by the Sun's glare. However, solar storms saturate the interplanetary medium with background noise, rendering faint objects more difficult to detect, akin to trying to spot a candle during a fireworks display. The signal-to-noise ratio collapses. For observers on Earth, the primary benefit of solar storms is the resultant auroras. If a coronal mass ejection impacts Earth's magnetosphere around the 20th or 21st of October, auroras may be visible at unusually low latitudes. Normally confined to polar regions, intense storms can extend the auroral oval to mid-latitudes. Individuals in the northern United States, southern Canada, or northern Europe might witness ethereal curtains of green, red, and purple light dancing across the sky. This spectacle is beautiful and serves as a potent reminder that space is not empty, but a dynamic environment filled with plasma, fields, and energy. Solar storms also carry a more ominous aspect. Power grids are susceptible to damage from induced currents. In 1859, the Carrington event, the most powerful solar storm on record, generated induced currents so potent that telegraph systems caught fire. A similar Carrington-level event occurring today would inflict catastrophic damage upon modern infrastructure. Economic repercussions are estimated to be in the trillions of dollars, with recovery taking years. While we possess better preparedness now than in the 19th century, our dependence on electronics has also significantly increased. Satellites, GPS systems, and communication networks are all vulnerable. NOAA's warning for October does not forecast a Carrington-level event, but does indicate heightened activity, with minor to moderate storms anticipated. This implies potential satellite disruptions, radio blackouts, magnificent auroras, and interference with astronomical observations precisely when clear data is most desired. The narrative linkage between Atlas and solar storms is tenuous yet compelling. Both phenomena involve the sun, and both are expected to peak concurrently. Both introduce uncertainty into our observational capabilities. Is the sun deliberately concealing Atlas? Assuredly not. The sun lacks sentience. It is a celestial body governed by plasma physics. However, this alignment, yet another in a series of coincidences, contributes to the perception of October 2025 as a period of intense cosmic activity. The theme of invisibility also resonates. Atlas is obscured by its position behind the sun, while solar storms create a different form of obscuration through interference and noise that impedes observations. Even objects that should be readily detectable become harder to discern. When the electromagnetic environment is volatile, invisibility manifests in multiple ways, geometrically, spectrally, and temporally. Sometimes visibility is hindered by an obstruction, at other times by overwhelming activity. Regardless of the cause, the consequence is the same: a lack of knowledge. If you find yourself observing Comet Lemmon or Comet SWAN around October 20th, it is advisable to check aurora alerts. Various applications and websites provide real-time space weather forecasts. Should a storm be inbound and the KP index spike, seek a location with minimal light pollution and observe the northern sky. You might witness an extraordinary display. While marveling at the auroral illumination, remember that these lights are caused by particles originating from the sun. The same sun currently obscuring an interstellar visitor. The sun bestows and the sun withholds. Currently, it is withholding our view of something we desperately wish to observe. Soon, we will shift our focus from solar storms to black holes, from our nearest star to the galactic center. Yet, the underlying theme persists: signals, noise, concealed messages, phenomena that we cannot directly perceive but can infer from their residual effects. The universe is replete with imperceptible information, and our task is to learn how to interpret it. Part 14. Studies of Black Hole Echoes. While 3 Atlas remains hidden behind the sun, astronomers investigating the opposite extreme of the cosmic scale have reported a remarkable discovery. New observations of Sagittarius A, the supermassive black hole at the heart of our galaxy, reveal evidence of X-ray and radio echoes. These are signals that rebound, persist, and reverberate across vast expanses of space-time, leaving detectable traces long after the initial event has occurred. Sagittarius A, often abbreviated as ESCA A, is located approximately 26,000 light-years from Earth within the constellation Sagittarius. Indeed, the very constellation that has repeatedly featured in our narrative. The black hole itself possesses a mass equivalent to roughly 4 million suns, compressed into a region smaller than Mercury's orbit. It is comparatively quiescent for a supermassive black hole, not currently consuming vast quantities of matter, but it does exhibit occasional flares, and these flares leave residual evidence. The echoes under investigation originate from material accreting onto SGR-A and potentially from a feeding event that occurred decades or centuries ago. As matter spirals into a black hole, it reaches temperatures in the millions of degrees, emitting X-rays. Some of these X-rays propagate outward and reflect off surrounding gas clouds. Due to the varying distances of these clouds, the reflected light arrives at different times, creating observable echoes, delayed images of past events, light that has taken a circuitous route. This phenomenon is known as a light echo. It is not exclusive to black holes. Supernovae and variable stars also produce light echoes, as do any transient events that illuminate surrounding material. However, black hole echoes are particularly significant as they probe the very fabric of space-time. The way light bends near the event horizon and how time dilates leave discernible signatures within the echo patterns. By studying these echoes, astronomers can map the environment surrounding the black hole and test the principles of general relativity under extreme conditions. The relevance of this to our Atlas narrative lies in the concept of echoes as delayed signals, information that persists and becomes accessible long after the original event has passed. If we consider interstellar objects as potential messengers, they might function similarly, not by transmitting real-time signals, but by leaving behind traces, signatures, and physical evidence that can be detected retrospectively. A probe does not need to actively transmit. Its mere existence, its passage, and the evidence it leaves behind are sufficient. This evidence can manifest as an echo in its trajectory, composition, or any accompanying artifacts. The connection to Sagittarius is also noteworthy. We consistently return to this constellation. Atlas is approaching from the direction of Sagittarius, and the WOW signal also originated from Sagittarius. The galactic center, the gravitational nexus of the Milky Way, resides there. When mapping galactic structure or endeavoring to comprehend the flow of matter and information through the galaxy, Sagittarius occupies a central position, serving as an anchor point and a frame of reference. Some speculative theories, and it is important to emphasize their speculative nature, propose that gravitational wave echoes from black hole mergers might induce persistent perturbations in space-time. These perturbations could theoretically influence the trajectories of objects traversing specific regions, potentially creating corridors or pathways where travel is facilitated or rendered more predictable. This is a fringe concept, not universally accepted within mainstream astrophysics, but it is undergoing mathematical exploration. If such corridors exist, they would logically connect to regions near massive gravitational sources like the galactic center. This concept aligns with the corridor hypothesis previously discussed. If objects follow gravitational pathways shaped by black holes and dark matter, then the echoes observed from S-rays might be integral to a broader cosmological picture. Signals reverberating through space-time, objects traversing routes carved by gravity, and information propagating across the galaxy, not as electromagnetic waves, but as physical motion through structured space. There is also a temporal dimension to consider. Echoes are fundamentally linked to time. An event occurs, time elapses, and the echo is detected. For black holes, this temporal span can range from years to centuries, depending on the geometry of the reflection. For interstellar objects, the timescale is even more extended. An object might be ejected from its home system millions of years ago, traverse the galaxy, and eventually reach our solar system, where it is detected. In essence, we are observing an echo of the event that created the object, perhaps a supernova expelling debris, a planetary system disrupted by a passing star, or even a civilization launching a probe. The object itself serves as the echo, delayed information originating from a distant event. If Atlas is artificial, if it is a probe, then it represents an echo of an intelligence that may no longer exist. The civilization that constructed it could have ceased to exist thousands or millions of years prior. The probe continues its journey, carrying its message and purpose, oblivious to whether its creators still persist. It is a sobering contemplation that we might detect evidence of intelligence that has already vanished, that first contact could be with a phantom, an artifact outliving its creators. However, even natural objects can be viewed as echoes in this context. Comets are remnants of solar system formation, and interstellar comets are remnants of the formation of other systems. Every celestial body, regardless of its composition, tells a story of the past. Astronomy is, in essence, the study of echoes. We do not witness events as they transpire, rather we observe them as they were, millions or billions of light years in the past. The universe we perceive is a vast repository of echoes, frozen moments arriving in sequence. The black hole studies underscore the principle that information persists. It bounces, it conceals itself, and it reemerges. Light that appears lost can be rediscovered, reflected off distant clouds, refracted by gravity, or scattered by dust. Nothing truly vanishes, it merely becomes more challenging to locate. With the appropriate instruments, methodologies, and inquiries, we can reconstruct past events from their residual echoes. When Atlas reappears from behind the sun, we will be observing not a light echo, but a motion echo. The object will have completed its perihelion passage undetected. Whatever transpired during that period is already history. We will witness the aftermath, the echo of that concealed event, and we will endeavor to reconstruct what occurred. This is akin to detective work, deciphering echoes and inferring causes from effects, the same process astronomers employ when studying black holes, supernovae, or the cosmic microwave background. The universe is filled with echoes. Some are comprehensible, while others remain elusive. Some are loud and apparent, while others are faint whispers requiring decades of observation and sophisticated analysis. Atlas is poised to add its echo to the cosmic chronicle. Whether this echo conveys a narrative of natural ice and rock or something more profound, we will only ascertain by attentively listening to what the silence reveals. Part 15. The reflection upon ourselves. As we conclude this narrative, let us turn our attention inward. We have dedicated 14 parts to examining 3 Atlas, posing questions about its nature, origin, and significance. However, an equally crucial question remains largely unaddressed. If we are being observed, would we even be aware of it? More fundamentally, are we prepared for such observation? October of 2025 is characterized by global discussions concerning autonomous decision-making in space, ethical considerations surrounding artificial intelligence, debates on the deployment of autonomous weapon systems in orbit, and strategies for managing space debris and satellite constellations. Humanity stands at a pivotal juncture, transitioning from a species that merely observes space to one that actively operates within it, constructs within it, and potentially engages in conflict within it. We are evolving into a spacefaring civilization, albeit in a disorganized and chaotic manner, lacking a cohesive plan or ethical framework. Consider the perspective of an external observer. Earth continuously broadcasts radio and television signals that propagate into space. Radar installations actively scan the celestial sphere. Satellite constellations reflect sunlight. Our atmosphere displays chemical signatures indicative of industrial activity, such as methane and chlorofluorocarbons, which would not occur naturally. We are conspicuous. We are visible. We are inadvertently advertising our presence. The Voyager probes, the Pioneer plaques, and our deliberate messages were intentional attempts to initiate contact. However, our true message is conveyed by everything else we do. The entirety of electromagnetic emissions, the cloud of satellites, the modified atmospheric composition. That's what an observer from afar would perceive initially. Not a deliberately composed communication, but the disorganized byproduct of a technological society that has failed to master discretion or efficiency. If Atlas is artificial, if it's present for observation, what does it perceive? A world in turmoil, grappling with environmental shifts, political unrest, dwindling resources, a species possessing remarkable technology, yet questionable judgment. We fissioned the atom and forged weapons. We linked the globe and cultivated echo chambers. We journeyed to the moon and then ceased further exploration. We are capable of extraordinary feats and equally capable of extraordinary folly. Would a sophisticated civilization desire interaction with us? That is not a certainty. Perhaps they would monitor from a distance, documenting, awaiting our maturation or decline. Perhaps they would intervene. Perhaps they would simply steer clear, categorizing our star system as overly volatile, too unpredictable. We lack this knowledge. We cannot acquire it. Yet the question holds significance as it shapes our perception of contact and our potential desirability as partners within a cosmic fellowship. Furthermore, there's the consideration of what we might be concealing, intentionally or otherwise. The vicinity of Earth is saturated with satellites, many of them unmonitored or inadequately catalogued. Debris from numerous launches, defunct satellites, fragments from impacts, all circulating in disordered clusters. From an external vantage point, this could be interpreted as defensive infrastructure, a technological shell encircling the planet. Is it protective? Is it indicative of paranoia? An observer would be unable to differentiate between legitimate orbital activity and militarization. Our own observational capacities are advancing at an accelerated pace. Telescopes such as the James Webb Space Telescope can scrutinize exoplanetary atmospheres for biosignatures. Future missions will directly capture images of Earth-like planets orbiting other stars. Within a few decades, we may identify industrial pollutants in an alien atmosphere, confirming the existence of technological civilizations without the need for radio signals. If we possess this capability, others likely do as well. The cosmos may be teeming with civilizations observing one another, deducing presence from chemical traces, all awaiting another to initiate contact. This presents a strategic predicament. Do you reveal your existence, risking unknown repercussions? Or do you remain silent, observing but not engaging, hoping to gather more intelligence before committing? Humanity has been inadvertently broadcasting its presence for a century. Our radio signal is expanding outward at the speed of light, now spanning over 200 light-years in diameter. Any civilization within this radius is aware of our existence or will be shortly. The decision has been made for us. We are detectable. Therefore, when Atlas reappears, when we scrutinize the data and attempt to ascertain its nature, we must recall that this evaluation is reciprocal. If it is observing us, it is also accumulating information. Our reaction to its presence, our level of technological advancement, our societal cohesion or lack thereof. All of this constitutes intelligence. We are being scrutinized, assessed, and evaluated, and we do not control the narrative. This underscores the importance of transparency. Why the debate concerning data suppression earlier is not merely theoretical. If we withhold information from ourselves, if institutions conceal data or postpone its dissemination, We diminish our capacity to respond effectively to cosmic occurrences. We fracture. We engage in wild speculation. We lose the thread of understanding. An advanced civilization observing us might conclude we are unprepared, not due to our technology, but because we are incapable of coordination, of shared information, of collective action. The other dimension is readiness. Are we prepared for definitive proof of extraterrestrial intelligence? Not in an abstract philosophical sense, but practically. Who speaks on behalf of Earth? Who determines our response? Do we respond at all? These inquiries have been debated for decades without resolution. International protocols exist, but they are not binding. In practice, if an extraterrestrial signal or artifact were detected tomorrow, pandemonium would ensue. Media frenzy, governmental pronouncements, religious reverberations, scientific disputes, all unfolding concurrently, pulling in disparate directions. Atlas may not be that catalyst. It likely is not, but it could be, or the subsequent object might be, or the one after that. The core point is that we must put our affairs in order before such a moment arrives. And by affairs, I refer to our collective comprehension of our identity, our aspirations, and our engagement with the universe that may be observing us. There is also the sobering realization that we may have already missed the opportune moment. If established civilizations populate the galaxy, if a network, a community, a set of norms and protocols exists, we are the newcomers, the boisterous, clumsy species that has just arrived. We are unfamiliar with the conventions. We do not speak the language. We are attempting to ascertain if anyone is present while broadcasting our ignorance to anyone who might be listening. So, what course of action do we pursue during the period Atlas is concealed? We observe, we wait, we prepare, we contemplate the implications of being part of a cosmos grander than ourselves. We acknowledge that the silence of space might not be vacant, but filled with dialogues we have not yet learned to perceive. We understand that observation is a mutual process, that outward gazing implies being seen. When Atlas reappears, when the data becomes available, we will analyze it with our most advanced instruments. Telescopes, spectrographs, artificial intelligence algorithms, human insight. We will strive to answer the question, what is this object? But we should also pose the question, what does this object perceive in us? Because if the perspective is reversed, if we are the ones under scrutiny, the view might be unflattering. And perhaps, just perhaps, that is the wake-up call we require. The heavens have always served as a reflection. We gaze upward and discern ourselves within myths and constellations. Ancient mariners navigated by the stars. Modern astronomers employ them to comprehend physics and origins. But now the mirror is interactive. What we transmit outward returns. What we observe might observe us in turn. We are no longer solitary with our reflection. Someone or something might be looking back. The three-eyed Atlas vanishes behind the sun. The countdown concludes. The quietude commences. And within that quietude we await not merely the object's reappearance, but the resolution of its significance for us, for them, for the universe that encompasses us both. Mark your calendars. Scan the night sky. Look for the Lemmon and SWAN tonight, should your skies be clear. Observe oriented meteors streaking across the heavens, and remember that somewhere beyond the sun, unseen and inaccessible, an interstellar visitor is forging history, accomplishing what no comet has ever achieved, reaching perihelion in absolute secrecy. And when it emerges, when we can perceive it once more, we will finally know if the weeks of darkness contained answers or merely further questions. Remain vigilant, remain inquisitive, and continue to observe the cosmos, for the universe is communicating. We simply need to learn to listen.